The title of this presentation is From Converse Results to Suitable Protocols for Mapping into the Authenticated Space. To begin with a presentation overview, as the third presentation of this series, we're further describing paradoxical aspects of quantum information. Building upon observations from the previous presentation and even the other presentation before that, the first presentation of the series, we now describe the three main results which describe and encapsulate how the converse result on the bit transmission rate impacts the protocols for encoding and decoding for Alice and Bob. And relatedly, it shouldn't surprise someone from a lot of the arguments and a lot of the intuition that I've been trying to establish for the viewer that the overlap function, it continues to play a role in defining probabilities and related probabilistic objects to error correction, false acceptance, and authentication. Excuse me. And then finally, the third bullet point, along with the ways in which prospective quantum advantage, particularly with regards to being able to simultaneously achieve error correction and authentication protocols with high probability can be achieved. And finally, before concluding the presentation, the next part of the overview, the fourth part of the fourth presentation of the series, which will be the final part, we continually draw the attention of the viewer to the statement of the three main results. We describe how protocols for mapping into the authenticated space of all cohorts with high probability continue to hold and remain resilient in the presence of noise. And altogether, this is allowing us to draw various comparisons to arguments previously provided from that presentation or that reference that I've mentioned throughout pretty much every presentation of the series due to Ostrov, under the assumption that the noise level between Alice and Bob's quantum channel is less than that of the noise between Bob and Eve's quantum channel. So it's pretty much demonstrating that we can have some aspects of quantum information which we could expect to hold when there's more noise over Bob and Eve's quantum channel in comparison to the noise over Alice and Bob's quantum channel. But in reality, what is really unexpected and paradoxical for the result relating in which we relate the converse result on the bit transmission rate to suitable decoding protocols which allow Alice and Bob to map into the authenticated space with high probability is that there's actually more noise over their channel in comparison to Bob and Eve's channel, which is really just demonstrating how unexpectedly we can still be able to garner quantum advantage even in the presence of noise, which is especially promising and especially important for maybe different types of algorithmic tasks, quantum algorithmic tasks, that is, or various information processing tasks that can be used to determine whether prospective quantum advantage or quantum supremacy, as maybe Google Quantum AI, IBM, and other types of big key leaders in the quantum computing industry and space have been discussing in terms of next generation devices that they've been trying to fabricate. In a previous result, like we mentioned in the previous presentation of this series due to Ostrov, which describes and details protocols that Alice and Bob can use for mapping into the authenticated space with high probability. Namely, I just reproduced this result from the previous presentation of this series in which it's really describing the existence of suitable protocols for Alice and Bob so that bit code words transmitted into the quantum channel can be mapped into that set of authenticated messages or authenticated classical n-bit code words or even code words with infinitely many bits as the number of bits tends to infinity, which holds with high probability. And this is just really given by the fact that we're fixing two parameters which are really resulting in the probabilities, like say Bernoulli P and Bernoulli Q random variables, which are determining or corresponding to information that's being classical information that's being transmitted over the quantum channel. But once this classical information is input by Alice or Bob or even Eve from the corrupted messages that are obtained from her decoding or her encoding, that she hopes Alice or Bob will mistakenly accept, hence making the probability of false acceptance to be strictly positive. We're fixing these two parameters to be for Q to be potentially equal to 1/2 and P being less than Q. And then now we're taking the bit transmission rate to be upper bounded by the difference between the binary entropies, namely x log x plus 1 minus x log 1 minus x for Q and P, evaluating this binary entropy function at the probabilistic parameters or the probabilities Q and P, such that for some epsilon strictly positive that's taken to be sufficiently small for a sufficiently large n, namely a sufficiently large number of bits, there exists a decoding protocol, pi sub n, namely pi sub n acting on first coboards with finitely many bits n, which is identically E sub n D sub n, which is identically um, expressed in Ostrov's previous result as being related to Alice's policy for decoding n-bit code words, as well as Bob's policy for decoding n-bit code words. And then this protocol is particularly important and salient for us to describe because in the presence of less noise, it's describing how this protocol, given the sufficiently small parameter epsilon, can be used to map into the authenticated space script A sub R sub n, namely the authenticated space, which is taking into account the bit transmission rate over the quantum channel, which will allow Alice and Bob to implement, protocols for mapping into the authenticated space like we've been describing with high probability. And like we also described in the previous presentation of this series, we pretty much provided this pretty lengthy statement, which is describing the lemma, which is detailing and describing and providing for the viewer, quantifying some aspects of noisy error correcting codes, namely that there's some inverse monotonicity of the radius of Hamming balls for code words with respect to the channel noise. And like I even tried to describe for the viewer that I'm going to reiterate now, this type of result really isn't that surprising because if we have more noise over one quantum channel, it's going to unfortunately directly impact in a pejorative sense or not make it as accessible for Alice and Bob to construct Hamming balls with very large radii, which can encompass more possible code words rather than the classical bit code word that they just transmit over their channel. However, nevertheless, from the results and even the overview presentation in this slide that I provided for the viewer, in which I was talking about and drawing the attention of the viewer to the fact that this prospective quantum advantage that we've been describing from the bit transmission rate and the converse result actually holds in the presence of more noise. This is actually really demonstrating how, despite this potential disadvantage or this property of error correcting codes, namely with respect to the Hamming balls, script sub b sub 1 and script sub b sub 2, which are respectively taken around the coword script c sub 1 and script c sub 2 with each one of their radii. There still can be some very positive impacts of in terms of quantum information processing and prospective sources of quantum advantage that can be realized. And this is just really relaying to the fact that, as we described in the previous presentation of the series, the second presentation, the transmission mechanism script n sub p sub q between Alice and Bob's channel, as well as script n sub little n p sub q of between B and E from Bob and Eve's channel, um, is relating to the fact that for greater noise levels between Alice and Bob's channel in comparison to which is strictly dominating the noise level between Bob and Eve's channel, we have an up to constants lower bound, which is dependent upon the ratio of the noise of the two channels for these two conditional probabilities. And again, we described them in the previous presentation, but very briefly to reiterate, we're looking at two conditional probabilities where the first conditional probability that's given in the numerator of this expression is conditionally upon the fact that the code word C sub 1, the classical n-bit code word or or this is actually finitely many-bit code word for this case, is transmitted through the transmission mechanism over Alice and Bob's channel. And then also, as one would expect, the conditioning for the probability which is appearing in the denominator of this expression is relating to the fact that the other classical bit code word with finitely many bits, again, it's transmitted through the transmission mechanism over Bob and Eve's quantum channel. And then, besides the conditioning that's given for these two conditional probabilities in the numerator and the denominator of this expression, we're looking at intersecting the code word superset, which is given by this little funny font script C, which is intersected with the first Hamming ball script B sub 1, as well as with the second Hamming ball script C sub 2, and we're basically providing some types of conditions about the cardinality or the total number of cowords that would belong or be identical or be common to the code word superset in each one of these two Hamming balls. And again, to finish off the statement of the of the result on the previous slide, the code word superset script C that we're using to incorporate into the event that's happening in the ratio of these two conditional probabilities that we're bounding from below up to constants is given by identically being equal to the union over all code words script C, another font for C, just for the code words, which is where this union over all of these objects, all these classical objects, these classical information theoretic objects, is an n-bit code word transmitted over the transmission mechanism between all Alice and Bob's quantum channel, as well as through the transmission mechanism between Bob and Eve's quantum channel, which is identically equal to just the union over the same number of n-bit code words, but taking also the union over bits, which allows us to pass to the infinite code word or to the infinite bit limit for code words that we can transmit over Alice and Bob's and Eve shared quantum channels. And like we talked about, the stability of the previous result for infinitely many bits entails that get as described through this corollary that we've also mentioned in this slide, but that we're just again briefly drawing the attention of the viewer to, is that we're having some type of stability result of the inverse monotonicity of the radius of Hamming balls with respect to channel words for code words for transmitted code words with infinitely many bits, which is just given by the fact that these two transmission mechanisms, as the number of bits tends to infinity, tend to some infinite to some analog of the transmission mechanisms over Alice and Bob's and Eve's quantum channels in the presence of infinitely many bits, which are corresponding to the channels across which code words with infinitely many bits are transmitted. And as one can expect, then the conditional probabilities are pretty much the same as what we had described in the previous slide. The only difference is that the conditioning for these code words can be allowed to take place for infinitely many bits, as well as just making use of the same definition of the code word superset that was given for finishing off the statement of the first property of noisy error correcting codes. So this is just pretty much demonstrating how we can still be able to take into account these, unfortunately, some of these proposed disadvantages of the quantum channels when we're performing this type of information processing task of sending classical bit code words over a quantum channel. But still, we can actually be able to quantify error correcting codes and what's the dependency of these codes for actually being able to describe and more precisely quantify proposed sources of quantum advantage. And the action of error correcting codes, like we also described, is given by a suitable class of error correcting codes or such codes which are given by this font script E sub C, which is the limit as the number of bits tends to infinity of the union of all codes for where we're looking at taking the union over codes for correcting n-bit code words, which has the effect of increasing the authentication probability of accepting the code word transmitted over Alice and Bob's quantum channel. Namely, the action of the error correcting codes which are lying within the suitable class is given by the fact that if we take some code word which is given by this C here, the error correcting code can act on this code word to produce another new code word C prime if and only if the limit as the number of bits tends to infinity of the n-bit code words C and C prime implies that the probability of C prime, namely the new code word that one obtains after applying the error correcting code to the original code word, has a higher probability of belonging to the authenticated set or the authenticated set of bit code words or authenticated set of messages over Alice and Bob's quantum channel in comparison to before we performed the error correcting code, which is corresponding to the lower bound for this probability that C prime belongs to the authenticated set, with instead just the probability that C belongs to the authenticated set. And just really to reiterate, the result for the strict upper bound for the converse result on the bit transmission rate that I obtained in my work is describing like we've pretty much been mentioning at every presentation of the series, because it's just a really interesting type of proposed source or prospective source of quantum advantage that we can quantify in terms of how many bits Alice and Bob would have to transmit per channel use. And which again is just given by the fact that we're taking a supremum in the expression for the bit transmission rate, we're taking a supremum over probability measures, and then we're taking a minimum between the mutual information entropy and the conditional Shannon entropy. And then finally, in the final minimum, we're taking a minimum over all possible letters, little z, that Eve can use for attempting to introduce some type of corrupted message into the authenticated space over Alice and Bob's channel, where respectively we're looking at H sub q, namely the conditional Shannon entropy taken with respect to the conditional probability distribution that Bob uses, subtracted from the Shannon entropy, the conditional Shannon entropy that's taken with respect to the conditional probability distribution that Alice uses. And again, we pretty much provided some type of very complicated expression, pretty complicated expression in terms of logs, and logs. And then I pretty much drew the attention to the fact that this is pretty much determining whether prospective quantum advantage can hold by generalizing the counterexample due to Ostrev, which was pretty much talking about the fact that Alice and Bob can be able to achieve some prospective quantum advantage, and that moreover, they need not sacrifice their probabilities of error correction and authentication being able to occur with high certainty or with high probability by basically conditioning their responses so that they use certain letters of their alphabet that Eve would never use. So basically, the pruned alphabets, like I described further and like I've described in the second presentation of the series, but it's also fleshed out a little bit and described a little more in the upcoming preprint, is that you can look to remove some letters from the original alphabets for Alice or Bob with the star alphabets, which is just pretty much potentially making the number of letters or the total number of letters in their alphabet smaller, so that with smaller probability, Eve will not be able to use some of their letters when she's trying to send some message that's been compromised from the channel that she shares with Bob over to Alice and Bob's quantum channel. And again, this is given by the expression, the identical expression for the bit transmission rate R. And again, the generic statement of the converse result is given by this, which we've been talking about and which has the same type of form independently of the specific case of the bit transmission rate, the strict upper bound of the bit transmission rate that's given in the previous slide. And in the beginning of the proof of theorem 1, like we described for the viewer in the previous presentation of this series, we established the following observations for obtaining this upper bound for the bit transmission rate from the converse result, which is just basically given by the fact that we're still starting out with the supremum over probability measures, and then the minimum between I and H, and then we're taking also a minimum again over the conditional Shannon entropies, which we can strictly upper bound with the logarithm of this supremum, because that's just the logarithmic function, the natural log. It's a monotonic function, just whatever number you take or whatever number you take of the natural of the log, as long as it's positive, because entropy itself is strictly a positive quantity, because obviously even very small systems have positive entropy from the potential degrees of freedom that these systems can have and can assume. And then this is just being identically equal to the supremum of the min of the log distributing the log to each one of the two arguments, namely the minimum of the log of the mutual information entropy, as well as the log of the minimum of the difference of the two conditional Shannon entropies, as well as also being identically equal to just basically also bringing in the log within the min. So just basically the log of the min of z is the min z of the log, as well as being able to strictly upper bound again by subtracting the log of the two conditional Shannon entropy terms. And then finally, in the last slide on this transparency, being able to strictly upper bound this last supremum term in terms of the final expression, namely looking to decrease the entropy of the second the strictly positive value of the second conditional Shannon entropy by incorporating a pruning or a pruned version of Alice's pruned alphabet, just mainly looking at an alphabet in which some prospective quantum advantage can be achieved by removing some letters, which is hence decreasing the entropy of that term, which is hence increasing the value of this minimum, because we're subtracting off a smaller term from the log of the conditional Shannon entropy of HP, a log of HP of y star conditional upon x, in comparison to the logarithm of the conditional Shannon entropy that's given in the previous slide or the previous line, namely HP of Y given X. And now, as we've been seeing, we can establish a lot of types of comparisons between the conditioning and the Shannon entropy because just basically there's a difference in the conditioning of the two Shannon entropies, which is appearing in that minimum over Z because one of them is looking at just basically like we've been describing the potential letters which Eve could use to try to compromise the authentication in the transmission protocols that Alice and Bob are using, and even obviously also their encoding and decoding protocols for classical bit code words over a quantum channel. But we also have to make use of the following expression for the minimum of the logarithm of the cardinality of two alphabets, which again is just given by this straightforward expression. And this is just relating to the fact that pretty much we can use the logarithm of the size of the alphabets of the players, namely the original alphabets or the pruned alphabets with some letters removed, because we can just basically look to relate into strictly upper bound the conditional Shannon entropies and the mutual information entropies, as well as so that when we're taking the supremum over this probability measure, which is appearing in the outermost bracket of that expression for the bit transmission rate, we can obtain the desired upper bound in terms of those contributions from that log-log factor plus the log factor. And we're going to provide now just explicitly all of the statements of the results so that the viewer can kind of understand and come to terms with all of these aspects of quantum information processing and quantum information theory that I've been describing and how that basically relates to all of the comments that we've been making in the past two presentations of the series. So this is just a statement of the first result, which is just exactly how it's appearing in the upcoming preprint, namely Theorem 1. The converse result on the bit transmission rate R for communication between Alice and Bob over a noisy quantum channel. And one has that the converse result for R star holds, where star is given by the expression in terms of those log and log factors that I've given in the previous slide, and pretty much it's been in every presentation of the series. So basically, one has that this converse result for the bit transmission rate holds, and under this strict upper bound for the bit transmission rate, Alice and Bob can guarantee that with arbitrarily small probability, the decoding and false acceptance occur. So pretty much there's an additional chance, or there's an additional aspect of this theorem, which is resulting from the favorable properties of noisy error correcting codes that I described for the player or for the viewer previously in the presentation, in which pretty much these two players or these two participants in this information processing type of game, they can be able to ensure that their probability of false acceptance as well as probability of performing a decoding error can be made to occur with arbitrarily small probability. And then the statement of the second result, this is a little bit more complicated, so let's zoom in to break down some parts of it. So the second theorem is given by a stochastic domination of the error correction and false acceptance probabilities for communication over quantum channels between Alice and Bob and between Bob and Eve. And again, this is just relating to a lot of comments that I've been making and observations from the previous two presentations of the series, in which I pretty much provided an expression for the viewer about what's the way that one can relate the probability of error correction over Alice and Bob's quantum channel to the probability of error correction over Bob and Eve's quantum channel, and actually how this former probability over Alice and Bob's quantum channel, it strictly dominates, stochastically dominates. In fact, it's a stochastic domination because it's between probabilities between Bob and Eve's quantum channel. And this is just given by the fact that we have to fix the following two parameters as given at the top of the statement of the second main result in Theorem 2, which is namely the noise over Alice and Bob's quantum channel and the noise over Bob and Eve's quantum channel, respectively, n sub A of B and n sub B of B and E. And then we're under the assumption that there's more noise over Alice and Bob's quantum channel in comparison to Bob and Eve's quantum channel. And we're going to denote the following probabilities, namely the probability of error correction, which is just over Alice and Bob's quantum channel, which is just given as the supremum of the probability of error correction or little e sub c belonging to the class of all suitable error correcting codes, which is given by the supremum of the success probability that the player using an error correcting code over Alice and Bob's quantum channel. And similarly, we can look at the probability of false acceptance, which is the infimum of the probability of all instances of false exception little f of A, which is given by the infimum explicitly and identically of the failure probability of a player accepting a message that should have not been accepted over Alice and Bob's quantum channel. And also relatedly, how we define the probability of error correction and the probability of false acceptance over Alice and Bob's quantum channel, we can also define the probability of error correction in the probability of false acceptance over Bob and Eve's quantum channel, because after all, we want to be able to lower bound the counterparts for the probabilities of false acceptance and error correction over Alice and Bob's quantum channel over Bob and Eve's quantum channel. So just basically, we can define these probabilities, and we're looking to, like how we've been describing through this statement, a stochastic domination result that's holding resilient to that is resilient to noise, and it holds in the presence of noise. And we're continuing the statement of theorem 2 just to provide the two stochastic domination results from these probabilities of false acceptance and error correction that were defined in the previous slide. So pretty much we're also defining some other probabilities which are relating to the decoding error probability, which can be made proportional to the false acceptance probability, because pretty much they're obviously not mutually exclusive. I mean, it's not like one probability happening will always occur or will always imply that another probability happens, but pretty much a false acceptance probability could be very well tied to and be proportional to a decoding error probability, which is given by the first line, which is saying that the decoding error probability over Alice and Bob's quantum channel is identically being equal to the supremum over all instances little d sub b of a decoding error over Alice and Bob's quantum channel, which is reflecting upon the decoding error probability of a message transmitted over Alice and Bob's quantum channel. And similarly, as one can expect, as I drew the attention of the viewer to in the previous slide in this presentation of the series, because we looked at probability of error correction and false acceptance for Bob and Eve's quantum channel from Alice and Bob's quantum channel, we can also introduce some type of decoding error probability over the channel that Bob and Eve share. And now, finally, this is the punchline, and this is the main result and the upshot is that one has that the following stochastic domination of error correction and false acceptance probabilities hold. Namely, like we've been saying, that the probability of error correction, despite the fact that there's more noise over Alice and Bob's channel, strictly dominates and constitutes the first stochastic domination, with the probability of error correction over Bob and Eve's quantum channel, in addition to the fact that there exists some C prime in R such that the probability of error correction to the probability of false acceptance both over Alice and Bob's quantum channel is bounded up to constants by C prime. I mean, this is just really identical to saying it's bounded, or it's bounded, it's bounded below by C prime, but I just like to say up to constants. Oh, actually, sorry, I changed it. Sorry, because in a previous version I had up to constants, but I changed it. But yeah, it's just bounded below by strictly positive real constant. So again, this is just providing and demonstrating the types of probabilistic nature of quantum information and how we can pretty much incorporate probabilities into our information processing tasks for classical bit coverts that are being transmitted over a quantum channel. And finally, we're going to end up with the third statement, which is the third final result, which is the statement of Theorem 3 in the upcoming preprint, which is given by the fact that Theorem 3 states that, or asserts, the existence of suitable protocols for Alice and Bob so that bit coverts transmitted over the quantum channel can be mapped into the set of authenticated messages with high probability. So we're fixing the same probabilities P and Q that we described in a previous result, like what Alstrev had used, but we're flipping the direction of the inequality between the bit transmission rate and the difference of the the difference between the two binary entropy functions. And again, it's just saying that for some strictly positive epsilon that can be taken to be sufficiently small for potentially infinitely many bit cohorts, we're asserting the fact that there exists a suitable protocol which is taking a similar form as what Ostreb had provided, except that again, the direction of the inequality between the bit transmission rate and h of q and h of p is reversed because that's compatible with the converse result from the strict upper bound on that bit transmission rate that we've been providing in the first main theorem, Theorem 1. So this is just basically saying again and asserting the fact that with high probability, there exists protocols such that Alice and Bob can map into the authenticated set of sequences even in the presence of noise with high probability. And as the number of bits little n tends to positive infinity, the policy, the decoding policy that is, of Alice and Bob takes this form, namely just taking the same type of expression but just having infinity to correspond to infinitely many bits that can be transmitted in code words. And we upper bound the minimum of the mutual information in the Shannon entropies, which is again coming into play in the result in the arguments for the first theorem, because we're looking at potentially the mutual information of I of X star and Y star, or I of X star Y star, or which can also be related to the minimum over Shannon entropies, namely minimum of H of X of Y star, or minimum of H of X star H of Y star. So just basically, again, this is just reflecting upon the fact and reiterating a previous comment that I made in this presentation in the series, from the perspective that we're looking to relate the conditional Shannon entropies and the mutual information entropies with strict upper bounds from the logarithm of the sizes of alphabets of different participants in this type of information processing task or game we can call even, whether it be Alice, Bob, or Eve. And from remarks in the first presentation of the series, we introduced the following conditions on the overlap function, namely the fact that the overlap function, as we're saying here, the limit as the cardinality of Alice's alphabet and the cardinality of Eve's alphabet each tend to positive infinity. We're taking some strictly positive constant C star star, which we're letting to tend to zero from above, and we're taking the supremum over all error correcting codes, over Bob and E's quantum channel, over all instances little f sub a of false acceptance within the collection of all instances of false exception big F sub a. And just basically, we're looking at a stochastic domination between the conditional probability that for all C star star strictly greater than C star, strictly greater than C star, which is a real constant, there exists some error correcting code such that the probability of error correction for this instance of an error correcting code occurs with positive probability, given the fact that the overlap between Bob's alphabet and Eve's alphabet is strictly greater than C star star. And this is greater than just the same type of conditional probability, with instead the threshold for the overlap function being taken as C star star instead of C star star star. And recall the decomposition of the overlap function over Bob and Eve's or Bob and Eve's alphabet, which is just again really helping us generalize that counterexample that was provided by Ostrep, in which we're looking at the union over little x, little y, and little z, where each one of these letters can be taken to be elements of the respective alphabets for Alice, Bob, and Eve. And we can also formulate restrictions of the overlap function, which again is just really getting at the fact that we were looking at ways to relate the probability of error correction over Alice and Bob's quantum channel to the probability of error correction over Bob's and Eve's quantum channel. And it's pretty much relating to the fact that we can restrict the overlap function to be able to basically relate the overlap function of like, three alphabets to the overlap function of two alphabets, or even to the overlap function of one alphabet, which is given by these two identical expressions on the slide. Namely, the fact that if we're looking at the overlap function of x, y, and z, but we're taking the first alphabet x, boldface x, to be identically equal to the empty set, namely corresponding to the fact that it has no letters. This is just being identically equal to the union over little y and little z of letters little y and little z in boldface y and boldface z, as well as also, as one could expect, if you just take another component or another alphabet from the overlap function to be identically equal to the empty set, that's going to also be able to be expressed in terms of the union over just little x and little y that are taken from the first two alphabets. And the decomposition of the overlap function in terms of the overlap function of individual alphabets can also be useful, because we're pretty much saying again that besides the restriction to taking certain alphabets to be the empty set that we provided in the previous slide in this presentation, we can also look to express the overlap function over little x, y, and z in terms of little x and little y union with little z, or this is also equivalent to the overlap function over little y and little z with little x separately, or also, sorry, I forgot an equality here, but this is also related to little x, little z, and little y. So basically, this is a way that we can relate the overlap function in various different forms to each other. So recap is that now to before we're moving on to the last presentation of this series, we describe the three main results together. They include Theorem 1, an explicit upper bound for the converse result on the bit transmission rate, as well as Theorem 2, a stochastic domination result, two of them to be specific, which are dependent upon the error correction and false acceptance probabilities over these two quantum channels of interest that we've been describing. And finally, Theorem 3, noisy protocols for mapping into the authenticated set of bit codewords with high probability. And so altogether, these three main results together allow us to characterize novel aspects of error correcting codes, authentication, encoding, decoding, and transmission protocols. In the next and final presentation of this series, in the upcoming part, we're going to characterize the main arguments and important areas of quantum information theory described in the previous three presentations. And thanks for watching.